The last time we introduced the concept of the Witten's scaling hypothesis, which will lead to a collapse of this scaling functions in terms of this combination of those parameters and in a power law fashion. So today we will continue using that scaling hypothesis to derive all the other scaling relations that we introduced last time. And we also formally study the origin of this scaling, why the scaling even occurred, and what is the principle behind the scaling phenomena. So let's just start by introducing a scaling form of free energy density. So last time we introduced the Witten's idea of scaling hypothesis for the magnetization, for example, and we use the scaling form for this magnetization, and we can derive some scaling relations, involving all these critical exponents, alpha, beta, gamma, delta, and so on. So today we will introduce other forms of the scaling hypothesis, which in some sense is more widely used, which is the scaling hypothesis for free energy density. Okay, so imagine that we are very close to the critical temperature, and the free energy density, which is the free energy per unit volume, shows some singular behavior, which may become singular in powers of this little t as t goes 0 to some power of 2 minus alpha, and that will lead to a singular behavior of all other, say, thermodynamic quantities, such as specific heat and magnetization and substitutability and so on and so forth. So multiplied by some scaling functions, capital F. Inside this argument, we have this external field divided by little t to the power of delta, which follow in some sense the Witten's hypothesis that this argument inside the scaling function is a kind of a combination of little t and these external parameters in a power law fashion. Suppose we can use that scaling hypothesis, we are able to derive different relations among all these critical exponents. For example, we could take this derivative of this free energy density following this scaling hypothesis, and we could derive this magnetization diverges at some power law in T when H, or external field, vanishes. And we can simply just take the differentiation of this Fs with respect to the H, external field, and then we could derive such a power law behavior. And we know that this has a particular power in the standard definition of the magnetization near the critical point, which is little t to the power of beta. But this beta should be compared with the left side of this T power law, and which is 2 minus delta minus alpha. So you immediately see that we have this relation. Beta is equal to 2 minus alpha minus delta, and we will use that in the later part of this derivation. So that's one relation. So we could also take the second derivative of free energy density with respect to the field. We get isothermal spin substitutability when H goes to 0 limit. Again, when we derive such a relation, we assume that it's both F prime, capital F prime, or capital F double prime here are well behaved when H goes 0. So then, in that case, we could immediately compare on two sides of this T power law behavior for isothermal spin substitutability, and we derive the second relation between gamma and alpha and delta. So we have these two relations, and we can combine these two, and immediately you can get rid of the delta, and you find that this relation or this equality holds, which is alpha plus 2 beta plus gamma is equal to 2. And this is the relation that we introduced last time. And this relation is actually particularly true for different kinds of critical systems. So it is actually valid for all critical phenomena that alpha plus 2 beta plus gamma is equal to 2. So we cannot violate this. And this comes from this kind of a thermodynamic stability condition that we don't have time to discuss. And remember, there's an inequality that this has to be bigger than or equal to 2, but near the critical point, this inequality becomes equality. So that's another scaling relations that we could obtain following this free energy density, a scaling hypothesis for this free energy density. So likewise, we can propose a scaling hypothesis for correlation functions. This is g r minus r prime, or g as function of this r, little t, and little h here, where r is the real space vector or distance between these 2 points for this correlation function. And remember, we have this form, discussed before, which is g is actually proportional to 1 over distance to the power of d minus 2 plus eta, and eta is non-zero. Remember that. But this correlation function, the Green's function, shows more scaling properties than just this power law, because it will multiply by a scaling function, which we call this capital F for this Green's function. And inside this capital F, the argument goes like r times t to the power of nu and h over t to the power of delta, and both parameters are dimensionless. So this correlation function, or all the other scaling function, is a function of all this combination of parameters which lead to the dimensionless parameters. So remember, this r to the power of times t to the power of nu is actually dimensionless because this r is actually the dimension of the length scale, and near this critical point, this length scale is actually correlation length, and this correlation length goes t to the minus nu as an exponent. As a result, r times t to the power of nu is actually a dimensionless quantity. So likewise, this little h is a dimensionless external field. When you divide this h by this t to the power of delta, it also reduces to some constant or dimensionless quantity. So this correlation function, the Green's function, near the transition temperature, goes like some distance to some non-trivial power multiplied by a scaling function. And this scaling function is a universal function of these 2 parameters, and these 2 parameters are dimensionless combinations of this little t and the distance, length scale, and also external field. Okay, so that's the essence of the scaling function. So we need both. We need to know the power law dependence of all these observables or correlation functions, but also need to know the behaviors of the scaling function, which will lead to a collapse of these data points if you plot this function against these 2 independent dimensionless quantity. So that's the idea of the power law dependence of observables and also universal scaling functions near the transition. So all these 2 properties can be combined into this kind of scaling form. So now we could discuss, so we will come back to this scaling of a correlation function in just a little bit later. But let's just ask this question. So what is the origin of the scaling? So apart from the smart guess proposed by Witten that he is able to write down in a very clever way a scaling form of magnetization both above and below the transition, but we could still ask the same question. So what is going on? Why do we expect to have such a scaling? What is the origin? So about this, we mentioned a little bit in the previous lectures, but let's just formally define or study and discuss the origin of the scaling. So all these non-trivial power law behaviors are originated from the principle that the correlation length diverges at the transition. So that's a statement that I emphasized many, many times in the very beginning of the course, but this is not sufficient. So we can say that the major cause that lead to this scaling is caused by the divergence of correlation length at the transition. But it's not the whole story, because if this is the whole story, then all the critical exponents will be the mean field like or follow from the Landau's theory, which is not accurate. We know that, right? So there's more to this origin of scaling. So to be more precise, this origin of the scaling comes from 2 facts. Number 1, the divergence of the correlation length, that's for sure. But there's a detail which involves the microscopic scales that we discussed earlier, and which also play a role here in the singular part of the free energy. For example, we could just write down the singular part of the free energy density in terms of the correlation length, because that's more or less the most important parameters or length scales of the problem near the transition. So we know that this goes like 1 over volume, and this correlation length is actually a length scale. So it goes correlation length c to the power of minus d multiplied by something else. But if you don't consider the microscopic scales, then this is just a prefactor a. And we know that this is not entirely correct. So there will be other corrections to this leading term, or capital A here. So the other microscopic scales involve, say, L1, L2, and so on. So depending on how many length scales or microscopic scales that you have. For example, we may have 2 different microscopic scales play a role here with a non-trivial power, which is L1 over c to some power sigma 1, or L2 divided by sigma to some power sigma 2. And those sigma 1 and sigma 2 are sometimes lead to some anomalous dimensions or anomalous exponents, which are yet to be determined. But the point is that we cannot just stop here without considering the other microscopic details, because that microscopic scales would certainly change the scaling exponents or the critical exponents. So we need to combine the divergence of a correlation length and some relevant microscopic details or microscopic scales, and only after this can we say that we fully account the origin of the scaling. Because the scaling comes from the divergence of a correlation length and also some power law dependence of some microscopic scales relative to the correlation length. So both are important. So let's take a short break. When we come back, we will follow this idea, and we could check the Green's functions near the transition and try to derive anomalous scaling dimensions or anomalous exponents from these considerations. Okay, so let's take a short break. So we continue deriving all the other relations following this kind of scaling hypothesis of free energy density, and plus this kind of combined factors that are important at the transition, namely the divergence of correlation length and also the involvement of the microscopic length scales. And so let's just come back to this free energy density near the transition in the scaling form, which goes like correlation length to the power of minus d times some scaling functions, which we don't care at this point. And because when we evaluate this specific heat exponent, the only thing that we need to do is just to take the temperature derivative second times the second derivative of free energy density with respect to temperature and multiply by temperature. And we know that c, the correlation length, goes like t to the power of minus nu near the transition. And so we plug that in, we get this power dependence of this little t for free energy density with exponent nu times d. So we take the second temperature derivative of this free energy density and multiply this by a temperature, you get specific heat, which goes like little t to the power of nu d minus 2, because you simply just take the differentiation of this Fs twice with respect to temperature, and that's it. And so by definition, this is t to the power of minus alpha, and alpha is naturally 2 minus nu times d. So in other words, this Josephson scaling law comes naturally from the scaling hypothesis for free energy density. And that is the relation that we could use with the help of scaling hypothesis for free energy density combined with the thermodynamic relations between the free energy density and all the other thermodynamic quantities. So let's just look at this scaling of a correlation length in K-space one more time to formally derive this so-called anomalous exponent. As I mentioned, this correlation functions involve some length scale and some scaling functions multiplied by some constant, say 1, plus additional contributions from this microscopic length scale, which we call L divided by c to some power of sigma. So this little g as function of dimensionless combination k times c is a scaling function that is unknown at this point, but we will determine this later. Okay? And a here is some kind of exponent that we need to fix and which involve anomalous dimension or anomalous exponent, and sigma is some kind of extra exponent coming from additional microscopic length scale involving in this correlation function. And this capital A is a coefficient which is weakly dependent on temperature, and we would like to recover this k-dependence form of this Green's function that we introduced last time, which is a k to some power with exponent minus 2 plus eta, where eta is kind of an anomalous exponent. So we would like to just compare these two forms between this well-known k-dependent Green's function and the scaling hypothesis of this correlation function. Okay, so to get to the pure k-dependent power law, we need to cancel this correlation length, c to some power of a. And so the way that we cancel out this correlation length dependence is to propose that this scaling function, g as function of k, c goes like x to the power of minus a, where x is this k times c. So with that assumption, we can easily cancel out this correlation length in the Green's function, the scaling form of the Green's function. And you could easily see that if I assume this is x to the power of minus a, and this is k to the power of minus a times c to the power of minus a, and this cancel with c some power of a, and therefore we get rid of the correlation length dependence, and we can show that this Green's function in momentum space goes like k to some power which is minus 2 plus eta. And you compare this power law exponents, you immediately see that this undetermined exponent is given by 2 minus eta. That anomalous exponents is determined primarily mostly from this kind of a scaling function, which involved in this correlation function near the transition, which goes like some power of k times c, and we could easily just cancel this correlation length right here. In other words, this correlation function goes like L squared c over L to some power a, and this L is again some microscopic length scale. Okay, so this tells us that not only does the correlation length appear in this Green's function near the transition, the microscopic length scale can also, in general, play a role here, and this is the example of that. Okay, so with that, we can easily verify that this kind of length scale dependence of this Green's function is actually consistent with what we derived last time, because then this g hat, which is the Green's function in k space, goes like L to the power of 2 minus a times k to the power of minus a, and you plug in this result, a is actually 2 minus eta, you get to this form, and this is precisely what we found last time, that the correlation function, the Green's function in k space near the transition goes like k to the power of minus 2 times some unknown function, which is kind of a microscopic detail or microscopic length scale, a, little a, in this case it's actually little l here, with a kind of a non-trivial combination of a times k or l times k as a dimensionless quantity to some power with some extra exponent eta. Okay, so in other words, this kind of non-trivial anomalous exponents come naturally from the scaling ansatz of correlation function over there. But we could check further the Green's function, the correlation function, when x goes to 0 limit, where this k is actually goes to 0 limit, which is the spatial average of this Green's function in k space. And we know that this is given by or proportional to this isothermal spin susceptibility, which goes like t to the power minus gamma. But we will do that following this scaling ansatz for correlation function. When x goes to 0 limit, we assume that this function behaves very well, which is simply just a constant. Then we could show that this is simply proportional to t to the minus nu times a, which is by definition t to the power minus gamma, and we immediately derive that this little a, which is 2 minus eta, which is given also by gamma divided by nu. So therefore gamma divided by nu is given by 2 minus eta. So this is another important relation among all those critical exponents. But in general, to find some kind of scaling ansatz or scaling hypothesis of some thermodynamic quantities, we need to first to find the dimensions of variables and to construct the dimensionless combination of those variables. For example, if there's a dimension 4 quantity which we call q, if q carry dimension of length scale of y, then this q is proportional to some length scale L to some power y, and therefore this q times c to the power minus y is a scale invariant dimensionless quantity. Therefore, we can actually propose or construct a scaling function based on this scale invariant quantity q times length scale to the power minus y near the transition. And that's the general principle that we can construct the scaling functions near the transition, that we first work out all this scaling dimension of all these variables, and we construct this dimensionless combinations of those variables, and the scaling functions is nothing but the function of those dimensionless variables. Okay, so that's the full story of this scaling and scaling hypothesis, and we will move on to the next chapter, which is about the renormalization group analysis, which gives the origin of this scaling from another perspective, namely from the RG flow. That's how do we know that those anomalous exponent, little a here, is really correct description of the transition, while the justification of such anomalous dimensional anomalous scaling behaviors comes precisely from the renormalization group analysis or the RG equations. So we will introduce the concept of the renormalization group and the kind of a block spin of a Hamiltonian and the scaling equation of the coupling constant under RG transformation. And we solve these RG equations, and we know how the coupling constant flow under RG. And then these critical exponents are simply the consequence of these RG equations. Okay? So it's a multi-layer subject. So we, at the very beginning of the course, we open up the phenomenology, but we don't know why. And then we offer a simple mean field like a Landau theory, but we need to go beyond Landau theory. And then we formally define all these critical exponents, but we don't know why. But suppose we understand the reason why we propose the scaling hypothesis, then we sort of can derive all sort of scaling equations and scaling relations, or this relations among all these critical exponents. But again, we don't know why. Okay, we know that suppose we propose such a hypothesis, then we can explain all the scaling relations pretty well. But the ultimate origin of scaling comes from the RG study. And this is the last topic that we will cover in this course, which is study how this scaling phenomenology and also scaling relations come about in the context of the renormalization group transformation. Okay, so let's take a short break. When we come back, we will formally introduce this scaling hypothesis and RG. So let's start a new chapter, which is the last chapter, which is about the scaling and renormalization group analysis and the relation between the scaling hypothesis and the RG. So we know very well that the mean field theory and the Gaussian approximations give, in many cases, the bad, very inaccurate critical exponents that we cannot improve anymore. And also, on the other hand, on an experimental point of view, we have the scaling phenomena. And as Witten pointed out, we have a scaling hypothesis which can combine all this data from above and below, and also from different, say, temperature fields and so on, and coupling constant, and they could collapse in a scaling regime. So the scaling phenomena is a real phenomena experimentally, and with help of a scaling hypothesis, we are able to derive all the scaling relations and so on. But what is the origin of a scaling relation or a scaling phenomena? And that should come from the RG analysis, which is what we are doing here. The beginning of this RG is the Kadanoff scaling hypothesis that he proposed in the 1970s, I think, to actually understand this coarse-grained Hamiltonian of an Ising model. And he considered a system, Ising-like system in d-dimensional hypercubic lattice, such as that to the lattice. For example, he considered rather than individual terms of the Ising coupling under a field, rather he will consider, as a group of Bloch spins as a basic unit in the Hamiltonian. Okay, so what the argument behind such a Bloch spin idea or coarse-grained representation of the Hamiltonian comes precisely from this phenomenology near this critical point or critical temperature, that the spins are correlated within this correlation length. Remember, near the transition, correlation length diverges, which means that all the spins or the observables are correlated by the same kind of a scaling behavior or power law behavior, no matter how far away these particles from each other. So based on this phenomenology and this kind of a correlated spins on the scale of a correlation length, so he proposed that maybe close to this critical temperature, the Hamiltonian itself could be decomposed in terms of the Bloch spin. So within each Bloch, all the spins act as if they are identical, as if they belong to the single unit. And of course, this factor B is greater than 1, which covers a group of spins, but not all the spins, of course, but just some group of spins. Within this each Bloch are considered to be a single unit. Namely, we are able to, so he proposed that we could take kind of a Bloch spin average and define the spins on the single Bloch or in the unit of the blocks by, again, taking the partial trace in a partition function over this individual Bloch, and we could rewrite this Hamiltonian not in the individual spin language, but in the unit of blocks. So that's the very beginning of the RG, which we sort of increase the system size from this lattice spacing to a group of lattice points. And then we start to increase further the length scale until the length scale reaches a thermodynamic limit. And as we keep increasing the system size or the block size, we monitor how this coupling constant flow as you keep increasing the size of the block. So that's the idea of Kadanoff, the coarse-grained Hamiltonian of an Ising model. And this sounds familiar because we already discussed the idea of a coarse-grained when we talk about the Landau's free energy over this coarse-grained variables. Remember that. And we could borrow the idea of this Landau's coarse-grained variables and to define the Kadanoff's coarse-grained Hamiltonian. In other words, we need to define this Bloch spin transformations and also the spin coarse-grained variables of the Bloch spin, or capital S, capital I, which is defined as simply just normalized the average spins over all these individual spins within this each block. So in other words, this M bar B is the average of magnetizations of these blocks by taking the sum of all these average spins on all individual sites inside this each block, and you divided this by the volume of this block. Okay, so this is MB. And so that this capital S, capital I is the block spin variable, the cross grain variable, is still normalized to plus or minus 1, the same way that we consider the Ising spin on each individual site, which is simply just plus or minus 1, depending on this is pointing up or down. But over the cross grain within this each block, we can define corresponding cross grain variables, which acts as if there's just a single spin. But this is not single spin. It's just effectively the spins of the whole block exactly work as a single unit that they point the same directions. So you can normalize this spin moment or magnetizations so that you could use a single spin variable. But this single spin is a normalized average spin, so to speak. Then you can count the total number of blocks as the total number of spins divided by the volume of each individual block, so that you can count how many blocks are there within your hypercubic lattices. And so next, we will actually introduce some kind of transformations between the original coupling constant and the rescaled the block spins Hamiltonian. Okay? And then we should find out the relationship between the coupling constant before we make such a block transformations and after we make these block transformations. Okay, so let's take a short break. So let's continue the Katanov's block spin representation of the effective Hamiltonian of the Ising model. As I mentioned, Katanov considered the block spin as a single unit near the transition because of the correlation length diverges, and many spins are correlated within a certain range in real space, so you can consider all the spins within each block act as a single unit. And based on this idea, he wrote down the effective Hamiltonian for a block spin. And there are two assumptions, very important assumptions of Katanov's idea. The first assumption is that the block spin interact only with the nearest neighbor blocks. For example, if this is the lattice with the block spin structure, and Si and Sj represents two block spins, and within each block, all the spins of individual sites are all the same, and they act as if they are a single spin. And therefore, this is natural to assume that the interactions for this effective block spin Hamiltonian shows only the nearest neighbor interactions between those block spin Si and nearest neighbor block spin Sj. In other words, when we talk about this block spin, what we already done is effectively we partially trace over the nearest neighbor interactions within each block. And then the Hamiltonian is simplified in terms of a block spin language. And the interactions are still there, so the natural assumption is that in such a block spin language, the interactions are only between nearest neighbor blocks. So you have this kind of a same structure as before, except now all the spins, individual spins, are replaced by the block spin. So you have nearest neighbor individual spin interactions over Ising coupling, but in the context of the block spin language, you also have this nearest neighbor block spin interactions. Because naturally, the interactions among all degrees of freedom are only partially traced in this block spin variable or representation. So there are still a leftover kind of interactions remains in the block spin representation of the Hamiltonian. And of course, you can imagine that, well, how about the second neighbor block spin interactions? We neglect that, or Kadanoff ignore that. And these kind of a further interaction distance, that kind of terms are not so important under RG. So we can justify the negligence of this second neighbor, third neighbor block spin interactions later within this RG argument. But let's just follow this Kadanoff's first assumption that within this block spin language, the Ising coupling can be rewritten in terms of the nearest neighbor block spin interaction. So then we can simply just rewrite this Hamiltonian in terms of the block spin coupling, which runs from this first block to the very last block with the nearest neighbor block spin. Okay, so the total number of blocks is given by capital N divided by b to the power of d, as I defined already. So then individual Ising term between nearest neighbor spins now is replaced by this block spin interactions. And likewise, the Zeeman term, the magnetic field coupled to spin, is also in unit of block spin language. So this HB is the effective Hamiltonian by using this block spin language, and this is of the same form as H0 as an initial Hamiltonian, except now the lattice spacing is enlarged by a factor of b, where b is larger than 1. So everything else is the same, except now we are using the block spin language. And so the coupling constant here, I attach this with a subscript b, refers to that this coupling constant is the coupling constant of the block spin Hamiltonian, not the original coupling constant of the original Hamiltonian. So there is a relation between Kb and K0. So we will demonstrate such a relationship later. But we just define, based on this Kadanoff's first assumption, that the block spin Hamiltonian is having the same form as the original Hamiltonian, except the coupling constant is renormalized and the lattice spacing is rescaled. But more than that, the correlation length is also rescaled under such scale transformations of the block spin representation of the Hamiltonian, because this HB measures the correlation length. Now in the units of the lattice spacing, but now the lattice spacing is enlarged to b times a. So therefore, the length scale is actually enlarged, and as a result, the correlation length of the block spin Hamiltonian is actually shrinked by a factor of b, because you can see very clearly that when you actually enlarge your lattice spacing, the effective correlation length is actually decreasing by a factor of b, because now everything is in unit of BA. It's like you actually enlarge your scale by a factor of 2, then everything's measured in units of 2, then all the length scale in the new units is actually scaled down by a factor of 2. Okay, so likewise, when you enlarge your unit cell by a factor of b, and b is larger than 1, then of course, if you use the U unit as your length scale, then your original correlation length under such a new units of length scale is actually reduced by a factor of b. So which means that this CB in this new unit cell is reduced by a factor of b respect to this original initial correlation length. So, but what does it mean? So it means that this CB goes further away from the critical value, which is infinity, because remember C goes like t to the power of minus nu, right? And it diverges when t goes to 0. But now, since CB is reduced by a factor of b, and the speed of the divergence is actually reduced by a factor of b. So in other words, this little tb, which represents the distance to the critical temperature in the block spin language, is actually larger than T1, where T1 is the distance to the critical temperature of the original system, okay, because of this relation here and that relation over there. So in the new unit, which is larger than the original one, the distance to the critical point is actually reduced. So we are further away from the critical temperature if we rescale this lattice in the block spin form. So in a similar way, so you could define the relation between the original magnetic field and the effective magnetic field of a block spin Hamiltonian, and this is the simple relation that you can simply just plug in the definition of this block spin variable S capital I, and also this m bar b, which is the average magnetization over entire block spins. And you can define this as a new effective field HB of a block spin Hamiltonian multiplied by this sum over this block spin variables S capital I. And this is the simple relation that HB is given by this original H times B to the power of D times m bar B. So we will use that later for the scaling analysis. So you can see that, and later we will also relate KB to this original Ising coupling K, okay, but that's the next step. So in a similar way, we could define the free energy density and to link the free energy density between the original Hamiltonian or original free energy and the block spin free energy, because we actually group together many spins over each block, and the original free energy density is given by little fs as function of a little t and little h, and the total free energy is given by this quantity times the number of spins. But now in this, the block spin language, we can also define the free energy density per block. So which I use this little tb and little hb as variables that this fs depend on. But the total free energy is given by this free energy density per block times number of blocks. So they should be equal, because whatever I calculate is the same system. So I could just count the individual energy of a per spin, but I can also count the free energy density per block and multiply by the number of blocks, and they should be equal. And so this is a very important relation between the free energy density in relation to the block spin language. And this is the origin of the scaling hypothesis. So we will see later that the origin of a scaling hypothesis comes precisely from Khatanov's rescaling of a free energy density in the block spin language. So that's the assumption number one. Assumption number two is that this little tb and this little hb carry a non-trivial scale factor, the power law exponent or power law dependence on the scale factor b in a non-trivial way, namely tb in relation to this original t by a factor of b times power of yt, and hb is given by h times b to the power of yh, where both yt and yh are positive exponents. Of course, this is some kind of a scaling assumption that near the transition, this little tb and little hb behave or transform under the scale transformation as some original t or h multiplied by a non-trivial power law in b. So it's rescaled. When we rescale this b, this distance to critical temperature and also this effective the magnetic field transform also in the non-trivial power law fashion with some non-trivial exponents yt and yh. And to confirm such an assumption, we should wait until we derive the renormalization group equations, and later by solving the renormalization group equations, we can justify why we make such assumption that tb and th and hb transform in a non-trivial power law fashion. So with that, we could combine all these two assumptions to write down the very important kind of a scaling hypothesis of free energy density in the block spin language, meaning before we group the spins into the blocks, and after we group the spins into the different blocks, the free energy density should behave in an equivalent way that they have a relation. The relation is the total energy is the same. Total free energy is the same, regardless whatever I organize all the spins, and but you will see all this coupling constant will flow under such kind of a rescaling of a length scale. But later we're going to derive this yt and yh by solving the RG equation, and then you could plug in this yt and yh, you could figure out precisely the scaling hypothesis that Witten proposed. So all these mysteries and kind of difficulties are resolved once we solve the RG equations. And so this is the key relation to link between the scaling hypothesis and RG. So we will continue with that kind of directions on Thursday. Getting more interesting because now everything actually links together. So everything that we talk about are all linked in that not so simple relation of a free energy density. So that's the power of our RG and also justification of the scaling hypothesis. So this completes all the circles here. All right, so I'll stop here and I'll see you on Thursday.